Hello! Welcome to today's lesson on the half-life and the randomness of radioactive decay. Today, we'll begin by understanding the randomness of radioactive decay, calling upon cooking analogies to help elucidate this concept. With this established, we'll move on to defining half-life and its significance. We'll also relate this to the stability of a radioactive atom. Imagine you're making popcorn in a microwave. You place a bunch of kernels inside, and as they heat up, they start to pop. It's impossible to predict which kernel will pop next. The popping of each kernel is random and spontaneous. This is similar to how radioactive decay works, where unstable atoms release radiation in a completely unpredictable way. Each radioactive atom has its own popcorn moment when it decays, and this moment isn't influenced by any external factors. Just like we can't predict which popcorn kernel will pop next, we can't predict exactly when a specific atom will undergo radioactive decay. However, while we can't predict the exact moment each kernel will pop, we can make a good guess about the overall process. For example, the popcorn bag might say it will take around 3 minutes for most of the kernels to pop. Similarly, in radioactive decay, we can predict the behaviour of a large group of atoms. We might not know when each atom will decay, but we can determine that about half of the atoms in a sample will decay within a certain time frame. This concept is known as the half-life in radioactive decay. It's like knowing that half the popcorn kernels will pop within those 3 minutes, even if we can't say exactly which ones or when. Half-life is a measure that helps us understand radioactive decay on a larger scale. It is defined as the time required for half of the radioactive nuclei in a sample to decay. Even though decay is random at the atomic level, half-life provides a predictable pattern for the behaviour of a group of atoms. Let's illustrate this with an example. Suppose we start with 200 radioactive atoms, and the half-life of this material is 10 minutes. After the first 10 minutes, half of the 200 atoms will have decayed, leaving 100 radioactive atoms. After another 10 minutes, 20 minutes total, half of the remaining 100 atoms will decay, leaving 50 radioactive atoms. This halving process continues over successive half-lives. So, after another 10 minutes or 30 minutes total, half of the remaining 50 atoms will decay, leaving 25 radioactive atoms, and so on. Half-life is not just a measure of time, it's also directly related to the stability of an atomic nucleus. A longer half-life means the nucleus is more stable, taking a much longer time to decay. On the other hand, a shorter half-life indicates a less stable nucleus, which decays more rapidly. For instance, consider polonium-210, which has a half-life of about 138 days. This relatively short half-life tells us that polonium-210 is quite unstable. Its atoms are prone to decay relatively quickly. In contrast, uranium-238, with a half-life of about 4.5 billion years, is much more stable. The extraordinarily long half-life of uranium-238 means that it decays very slowly over time, making it much less radioactive in the short term. This concept of half-life helps scientists understand and predict the behaviour of different radioactive materials. For example, materials with shorter half-lives might be used in medical treatments, where their rapid decay can be harnessed for therapeutic purposes. On the other hand, materials with longer half-lives, like uranium-238, are often found in geological dating, where their slow decay provides a clock to measure the age of rocks and fossils over billions of years. Understanding these concepts allows us to make sense of the seemingly random behaviour of radioactive materials and apply this knowledge in practical fields such as medicine, archaeology, and nuclear energy. In today's lesson, we explored the concepts of the random nature of radioactive decay and the concept of half-life. We began by understanding that radioactive decay is a spontaneous and unpredictable process, much like the random popping of popcorn kernels in a microwave. While we cannot predict exactly when an individual atom will decay, we can predict the behaviour of a large group of radioactive atoms using the concept of half-life. We defined half-life as the time required for half of the radioactive nuclei in a sample to decay. We also discussed the relationship between half-life and the stability of atomic nuclei, noting that more stable nuclei have longer half-lives, while less stable ones decay more quickly. In summary, although radioactive decay is inherently random, the concept of half-life provides a statistical framework to predict the decay behavior of radioactive substances over time. This understanding is crucial for applications in fields such as medicine, archaeology, and nuclear science.